And to Professor Paul Horowitz to introduce today's speaker. Paul.
I'm not today's speaker, I'm introducing today's speaker. Okay, so it's my great pleasure to introduce my good friend Rich Muller. I'm not good at introducing, so on the way back from lunch today, which Rich was regaling us with just incredible conversation about any topic on earth, I asked Erwin Shapiro, how am I going to do this? And he said, I got a quote here, there's so much he's done, the hard part is deciding what to leave out. So I think I'll just leave most of it out, and just the briefest of introductions, because Rich started life in high energy physics as a protege of the legendary Louis Alvarez at Berkeley. But he quickly developed a unique taste for what I guess I'd call the big problems, wherever they lay. And Rich was and is the founder or prime mover behind a whole bunch of really cool stuff. The cosmic microwave background anisotropy measurements, the cosine, radiocarbon dating using particle accelerators as extremely high resolution mass spectrometers. This is the standard technique these days. The Berkeley Supernova project to measure, as Rich put it, the deceleration parameter. What a surprise that the deceleration parameter turned out to be negative acceleration. He's followed these with interest in population extinctions, the Nemesis Death Star that causes bad stuff to come in from the Oort cloud, but luckily there doesn't seem to be a nemesis, but nice idea. Geomagnetic reversals, ice ages, climate change, air pollution, nuclear waste storage, we learned today. You can't have nuclear waste disposal. You have to be able to get it back. And the thing for which he was honored yesterday, a scientific literacy for people who do government policy, the books and the courses, Physics for Future Presidents, Energy for Future Presidents. Rich has won lots of cool awards, among them MacArthur Fellowship, the NSF Waterman Award, the Texas Instruments Founders Prize. He's written op-eds in places that real people read, the New York Times, the Washington Post, columns in the MIT Technology Review for several years, 10 books. I think of you as a serial masochist, having written one or two myself. And answers to hard questions. There's a website called Quora where anybody can ask anything, and Rich is evidently the most prolific answerer on Quora. I've known Rich now for 30 plus years, mostly in connection with scientific solutions to problems in national security, and I find him to be a bold and original thinker, always surprising, never boring, daring and fearless. Pick any topic you've thought about, and Rich has thought more deeply and has an unusual angle on it. You come away with your DNA tingling. It's really exciting. For a really random sampling, I asked Rich to give me a copy of a thing that he made about 15 years ago called Memory Book. This is to try to remember odd sorts of little facts. This is the October 2000 edition, so this is 15 years old. Here's some facts. This business about the speed of the acceleration of gravity, 10 meters per second. If you multiply it by the number of seconds in a year, multiply g times t, you get the speed of light, if it were Newtonian. But the way Rich put it here is so great. G equals one light year per year equals 1 light per year. I mean, how's that for weird? But that's kind of pure Rich. Tidal friction. Did you know that we lose 2.5 milliseconds per day per century from the moon slowing down the Earth by sloshing stuff around? Did you know that a megaton throws a megaton of dirt? Here's one attributed to me. Boron stops neutrons, passes gammas. Bismuth passes neutrons, stops gammas. Anyway. I must have known that once. Radon in your house is measured in picocuries per liter, and the action level at which you're supposed to do something is 4 picocuries per liter. Rich's fact is 1 picocurie per liter equals 1 cigarette per day. So if you have a clean basement, you can smoke more. Here's a cool one. Sheldon L. Glashow was on the Bronx Science Protozoology Squad. And Versailles cost $1.4 billion in 1982 dollars. And here's the last one, and then turn it over to Rich. It says here, I'll read it exactly, dental floss plus Ajax equals escape. You get it? 2 things you can have in a prison. Okay. On this last note, let's escape the bounds of conventional thinking with Rich's help. Please welcome our honored speaker, Professor Rich Muller.
Oh, thank you so much for that. But I will, of course, have to correct you. No, the Nemesis theory is not ruled out. And for those standing in the back, there are some seats here that are reserved. You're welcome to come down and sit in them if you don't mind sitting in the front. For some reason, people in my class never would fill up the front seats first. But there are seats down available in the front, which I will now officially release. So someday, you are going to be asked to give an historical lecture. And your response will probably be the same as me. Am I that old already? Well, as I think back on it, there are so many interesting things to say. And this is where I have been recently. This you can download from the web. It is our map of the temperature of the Earth versus time. Well, you can see the time there. And it's full of fascinating things. And there's global warming. But I'll be getting to this near the end. I put it on just to give you something interesting to look at, so you wouldn't have to pay too much attention to Paul. What I'm going to do first is get back to the beginning of my show. And what I realized, well, that's my favorite place. I went there on my second date with my wife-to-be. Okay. It's strange looking back, and I've had a very diverse career. I attribute that mostly to Louis Alvarez, who regarded there's no problem he didn't regard in his domain. If anything important happened in the world, if any important discovery was made in science, he would always say, do I know something that is relevant to this that maybe nobody else knows? And if so, he would start a project doing it. And I could now give a talk for a couple of hours about the wonderful things that Louis Alvarez did. But he was my mentor, and I paid a lot of attention to that. I want to go through, not all of my research, but I want to go through the research that led to my interest in global warming and air pollution. And I realize in looking back at this, since I'm supposed to give a historical lecture, that it's basically my research has been one catastrophe after another. And that's kind of amusing, and I'm not sure why that's the case. And it may simply be because kids love to play with explosives, and it really grabs your attention. But what I'm going to do, what I really want to talk about, though, is the stuff at the end, the global warming and beyond, particularly air pollution. So I'm going to try to go fast. And I'm going to start my timer. Let's see if there's a timer here. Where is the timer? There it is. OK. So I start the timer. And I'll go kind of fast over the history part, just so I'll have a little bit of time at the end to talk about the current catastrophes, the one that we are in the middle of right now. So my first catastrophe, actually my first catastrophe was my thesis project that crashed into the ocean from 70,000 feet. But let me skip that one. Experimental physics is tough, and that actually did teach me something. And later, when I got to the cosmic microwave background radiation here, as you'll see, I chose not to fly it in a balloon for just that reason. So the first catastrophe I will cover is the Big Bang. And in the beginning, the universe was full. I really should point, I guess, with the computer, since people are looking at different screens. In the beginning, the universe was full of gamma rays and electrons and positrons. And at one point, the electrons and the positrons cooled off enough that they formed neutral atoms. Now, a remarkable thing happened when that occurred. The light beams that were bouncing all over the place, suddenly, neutral atoms, they started going in straight lines. And if we just draw attention to those that happen to be in this shell, there they are, along with their neutral atoms. And these started going in straight lines, and I'm picking the ones that were headed towards where we would be 14 billion years later. And here's where the Earth will be, and they're on their way, and these are the ones that are coming in. And when we look at these photons, these appear on the Earth as cosmic microwaves. We call it the cosmic microwave background. The name background comes from a technical use in radio physics, but it's actually behind everything else. And we can look at these things now, and it was discovered by Penzias and Wilson in the 1960s. And when we look at it, we're getting a picture not only of the most distant part of the universe we can observe, but we're also getting a picture of the way it was 14 billion years ago. And that's fascinating, and I was fascinated. And in the 1960s, Penzias and Wilson had discovered the microwave radiation, and I was really wanted to get into this. I did my PhD thesis in elementary particle physics, but now I wanted to measure this. So I put some instruments together. I learned about microwaves. I went up on mountaintop, a white mountain, 1972. That's me. I haven't really changed. You can't see me very well there. And here we are using what's called a Dickey radiometer. So you're measuring the microwaves coming from this region and from this region, and you're comparing them back and forth. And what I wanted to do was to detect any variation, because Penzias and Wilson said it was uniform to about 10%. They could see that. It was uniform, coming from space. I wanted to measure it to better than that. And this was largely an exploratory experiment to see what the problems were. And the atmosphere turns out to be a big problem. There were some other problems, too. Here's a list of the other problems. This appears in my 1978, May 1978 Scientific American article I wrote on this project. And it's instructive, I think, that here are the problems that you had to think of before you did the experiment, and you had to have good solutions to do them. Then a few more always come along that you didn't anticipate, and you don't want that to be too many, and you have to be flexible enough and have good colleagues. We built an instrument that would satisfy those. There's a picture of it. This instrument is now in the Smithsonian Museum in Washington, D.C. So there is the instrument we built. Notice these strange horns. This is what's called an inductively apodized horn, and it was on that list before. It was pretty tricky. This is me and graduate student Mark Gorenstein. See, I haven't changed. Installing the instrument on the back of this airplane. Here's another picture. This one is interesting because at one point I went to a young physicist, he was a postdoc, who I knew and who I respected and who I thought was really super smart and very hardworking and very careful with instruments. And I went over to him and said, George, you know, we really need some more help on this project. Would you be interested in working on it? And he looked up at me and said, yes. Easiest recruiting job I ever had. His name was George Smoot. And he wound up winning the Nobel Prize some decades later. This is our U-2 airplane. It doesn't show the instrument on the back. U-2s usually look down. We had to cut a hole in the back, which is kind of tough because the skin is part of the structural element. So it was a big deal, but we made the measurements. I'm going fast because I really want to be able to get to global warming and air pollution. So in our initial flights, this is the fraction of the sky that we actually made measurements in. And we found a pattern that hadn't been seen before. It was a pattern that was expected, but it had never been seen. I call it the cosmic cosine. So if you look in the direction of Leo, the microwaves there are most intense. They're least intense in the opposite direction. Now, we didn't actually get to look in the opposite direction because that was below the equator. But we looked around, and this is a plot as a function of the angle to Leo, and you see it's a cosine. If we assume the whole sky is a cosine, this is also from my Scientific American article, this is what the sky looks like in microwaves, if your eyes could see microwaves. Basically an intense spot in Leo. This was expected because the Earth is in motion, the sun is in motion, the Milky Way is in motion. We were able to measure the velocity of the Milky Way by doing this. When you're running through the rain, you get more rain hitting the front of you than your back, and that's a cosine effect. So we were seeing the microwaves as we moved through them. What are we moving with respect to? We're moving with respect to the distant matter of the universe. Now, in relativity, there's no absolute frame. But this is the most absolute you get in relativity. It's the frame of the distant matter of the universe. We could measure the velocity of the Milky Way. It turned out to be a really interesting number. Very close to 1,000,000 miles an hour. I never forget that number because it's such a round, nice number. It's not completely out of whack with what was expected, but it had never been measured before. So we saw the cosmic cosine. New measurements from satellites have refined this, and here's the latest. And here the brightest is in Leo, and it's really nice to have your result from 1976 confirmed by modern satellite measurements and have basically within our error bars we got the direction right and the intensity right. That's always really nice when that happens. Now, we still didn't see any variation in that cosmic shell. And the cosmic shell existed and emitted these photons about 500,000 years after the Big Bang. And that's pretty early, and that's very interesting. So there should be some structure in it. So we wanted to do a more sensitive experiment. We needed about a factor of 30. To do that, you have to put it in a satellite. I thought about that and said, go ahead, George. I hate bureaucracy. And there is very little worse than NASA bureaucracy. Well, there's an NSF, Department of Energy, but this one, I decided to stay away. George, I knew, could do it. And so he took the instrument, he had to modify it, he got it, it was expected to fly 4 or 5 years after we began it. But then they canceled that satellite. They canceled it because for various different reasons, and they said, we want you to put it on a manned flight. And George's reaction was, no, God, you don't want me to put it on a manned flight. If it has to be man qualified, it's going to be far more expensive. The reason was they wanted to justify the manned flight. So they wanted to have good experiments to put on the manned flight. So he was forced to put it on the manned flight. That held it up another 5 years. And then there was the accident, and they canceled that. And they said, OK, we're going to put you on a different rocket, but now we want you to go on a rocket that's going to have several different instruments on it. You have to work in with them. 14 years after he started this, he got the results. So there is George, and there is Kobe, and there is the instrument. It's basically our instrument placed in there and then refined and fixed up a bit. There are things you can do in space that you can't do on the ground. And the results were, the original Penzias and Wilson just saw uniform to 10%. This line here of bright stuff, that's a map of the sky. That's the galaxy, and that's just in the way. So you have to ignore something in the galactic plane. In Kobe, he saw this pattern. He and all of his collaborators. He had lots of collaborators. These satellite projects get very big. Now, they don't only take a long time, they get very big. And this is the galactic plane, so ignore that. But here's real intrinsic variability. And Hawking called this the most exciting result he had seen in his life. And indeed, George was awarded the Nobel Prize in 2006. These are the more modern measurements, and we're beginning to see it's all consistent with what George saw, but now we're beginning to see lots of structure, and this is utterly fascinating. There's a lot of work going on there. We might be able to see early gravity waves and tell all sorts of interesting things. But that was my first catastrophe, was the Big Bang. My next catastrophe was the death of the dinosaurs. So as I was working on a different project, Louis Alvarez, who I was very close to at the time. In fact, here's a picture of him and his son. His son had found this thin layer right there of clay in which all the microscopic animals here were almost all gone above it. Some catastrophe occurred on that layer. And Walter speculated that it might be exactly the same layer where the dinosaurs disappeared. And that utterly fascinated his father, who before had found geology utterly boring. And so he and his son started collaborating. This is one of the great historic collaborations of all time. They figured out what had happened. Frank Asaro, Helen Michael joined the team. A whole story there. That's another hour I'm not going to go into because I didn't get into it for a few years. And then two paleontologists, Dave Ralph and Jack Sikowski, found a strange pattern of extinctions that it wasn't just the one that killed the dinosaurs, but there were lots of others. And the oddest thing about it was they seemed to be on a regular 26 million year cycle. Well, that led me into my own study of this catastrophe. Pete Hutt, Mark Davis, and I wound up coming up with an explanation. Lisa Randall, who may be here, has her own explanation today. This is a hypothesized star orbiting the sun that comes close, and when it does, messes up the comets and causes a comet shower or a comet storm. And this is what a comet storm would look like. A billion comets come in. On average, only one of them hits because the Earth is a small target. Maybe two hit. The comet, there could be several catastrophes at the same time. It's a fascinating story. According to Paul, this theory has been ruled out, but actually it hasn't. Because, as I'll come to in a moment. But here's a trivia question for you. You need to make a guess. What physicist earned his PhD with a thesis titled An Astrometric Search for a Stellar Companion to the Sun? In other words, a search for Nemesis. Who? It's someone you may have heard of. No, you have heard of him. Have you? No, you haven't yet, but you probably heard of him. Who did that? Anybody know? Nobel laureate Saul Perlmutter. Search for Nemesis. Almost nobody knows what Saul Perlmutter got his PhD thesis doing. I'm saying, has Nemesis been ruled out? And the answer turns out to be no, for reasons that have to do with the stability of the orbit. We can show that the orbit, to be stable, has to be in the plane of the galaxy. That's the only place we really haven't searched thoroughly. And therefore, we should not have found it if it is there, because these searches don't get into the plane of the galaxy. But very few people know that. And so if you look online, you'll see all sorts of people saying, well, we know the Nemesis theory isn't right, but I think it's still viable. It's up there competing with Lisa's new work. Why am I so confident that we will find it someday? Well, physicists are like other people. Sometimes it's a gut feeling. In this case, there was a historical event that leads me to believe that Nemesis will indeed be found. And this historical event, this is a history lecture, right, had to do with a dinner that Walter Alvarez had with the great geologist Gene Shoemaker. And the day after he told me, he said they were discussing Nemesis. And Gene was saying, I think Rich's star is there. And Walter was saying, well, it may be there, but I don't know if Rich's star is there. It may not be. It could be randomly happens to line up every 26 million years. And then Walter got his fortune cookie. And he gave me his fortune. The star of riches is shining on you. So, gotta trust a fortune cookie. Okay. More on the Big Bang. So, entranced with the Big Bang, with what we had learned, now the obvious question in physics, and it's hard to imagine a more important question than this. I mean, some people say origin of mass, what is the God particle? They have all their own favorite ones. My favorite one is, will the universe go on forever? And at the time that I had a new project I wanted to do, that one really intrigued me. And I went to a talk given by Robert Wagner, which talked about the possibility of measuring the expansion of the universe and seeing if it was slowing down. Now, normally, if you look at the expansion of the universe, you'd say, well, it's expanding, and it's expanding with a Hubble expansion, and that's it. But as you look further away, you're looking back in time, and you could see the rate of expansion back in the past. Now, what we all knew would happen would be because of the mutual gravity, the expansion in the past would be faster than it is now. Because we're slowing down because of mutual attraction. So it was called the deceleration parameter, and Paul mentioned that. And we could measure that using supernovas. So I got really excited about this, and I talked about the idea of it was using type 2 supernovas. And there's an hour talk here I could give about that. And I wanted to do this. And it would require making a telescope to automatically look at a large number of galaxies, detect these distant galaxies, detect supernovas in those distant galaxies, use those supernovas to tell how far away the galaxy was, use the Doppler shift to get the velocity, measure the Hubble law as a function of distance so we could see that in the recent time the expansion was slowing down. That's all we would have to do. So here I have a picture. I guess I have a picture of that. Here's the Hubble expansion with random galaxies. And as we go further away, we can measure the Hubble expansion. And we should see that as we go back in time, it was faster because of mutual gravity slowing us down. And here's an early picture. I got this project going here I spent 14 years on this project. And this is me blocking the telescope, but it's daytime. Nobody uses the telescope during the day. But this is our small telescope that we used. And we discovered automatically, we look at the same galaxies every night. We had a computer program that would check the images that we got, compare them to the images of a week ago, and look to see if there was a new bright star in them. If there was a new bright star, then we could tell the distance. I chose not to use type 2 supernovas because it looked too hard. Instead, we switched to type 1a supernovas. To do that, you would have to calibrate them because of little differences between them. But we had lots of ideas for ways of calibrating it. We'd accumulate enough supernovas that would be able to do this calibration. And then we'd have the distance of these distant supernovas. We would have the, after 14 years, Saul I'd hired him. Once he got his PhD thesis, I hired him to work on the supernova project. And I just remember 3 incidents. I went into his office and said, Saul, I know you've been thinking about this. Let me tell you a new idea I have and show you why this will really improve the supernova search. And he listened to me and he said, yes, well, Rich, let me show you my file on that idea. And here's why it doesn't work. Okay, thank you. And then a few months later, I came in and said, Saul, this is something new. You haven't been thinking about this. Let me tell you about it. Here's what we can do. I think this will really help. And he listened politely. Then he said, well, actually, I have thought about that. And let me show you why it doesn't work. On the 3rd one, I decided he should be in charge of the project, not me. And I would simply work on the side and help him. So we arranged for him to take over the project. Saul. So he took charge. That was about after he'd been on the project for about 6 years. And I kind of drifted away because I wasn't having any ideas. I don't like working on projects that I'm not really making contributions to. So he could do it. He could do it better than me. When you find someone who's better than you, there's great joy in that because it means you can do other things. So he went on, and a few years later saw the departure from the Hubble law. Hubble law would be, the ordinary Hubble law would be this line here, and he saw that they were drifting up from that. They were not fitting the Hubble. There, this is the Hubble law right here. They were drifting up. This was statistically significant. About that same time, another team, partly here at Harvard, was seeing a similar thing. They had started a search using basically the same thing we were doing, competing with us. And they found a very similar result. And was actually, what year was this? 2011. And I had started a project by that time. That was many, many, many years later. That was 11, 12, 13 years later. I'd started a project looking at global warming. And I'd asked Saul to join the global warming project. The supernova project was somewhat in the doldrums, and he joined the global warming project. I wanted him on because I knew he was hard-nosed, he was honest, he was objective. He would not let us come to any conclusions. And so we were writing the paper. Saul and I were writing the paper on the supernova thing. And it wasn't at that moment, but it was the next day that it was announced that he had won the Nobel Prize in physics for the discovery, not that the universe is slowing down, but that the universe is speeding up. No, we didn't anticipate that. No, nobody anticipated that. If I had still been working on the team, I probably would have said, no, you can't publish this. This is absolutely ludicrous. But fortunately, I wasn't still working on the project. And so he published it, and the Harvard collaboration published it at the same time within a few weeks of each other, a week of each other. And they both teams got the Nobel Prize. Here am I in Stockholm with Saul. He was awarded the Nobel Prize in physics for this fantastic discovery that the universe is actually speeding up. And does that make sense? Well, it turns out it can fit into general relativity very easily. But people are uncomfortable with that. And there's a whole story there and a whole another hour talk, which I don't have time to go into right now. So let me move on. But that's one of the greatest discoveries, I think, of the 20th century. So was the Louis and Walter Alvarez in figuring out what killed the dinosaurs. That has changed our feeling about the past. This changes our future about our feeling about the future. 2 years before he made this final discovery, I was teaching my Physics for Future Presidents class. And I said to my class, well, you know, I don't know if the universe will go on forever, whether we'll come back into a big crunch or not, but I believe that within the next 5 years we'll know. And the reason we'll know is that Saul is now leading this project, and they have come up with the critical ideas to make this a success. The key ideas were all due to Saul's. He's going to make it a success, and we're going to know. And then it didn't take 5 years. 2 years later, I was telling my class, yeah, we're going to be able to say, and then I got permission from Saul to let the class know what they had found. The universe is actually accelerating. That means it is not going to collapse. Unless something new happens 20 billion years from now and some new force turns on that didn't turn on before. But according to what we now understand, the universe will go on forever. Will life go on forever? Will interesting life go on forever? That's a great debate that's going on right now. But at least the universe will go on forever. Next thing was, we were looking back. This is Robert Rohde and I. Robert was my graduate student at the time. And we were looking at these extinctions, these mass extinctions that took place. And he decided to look at the fossil diversity. How many different families are there at any one time? So we had all this huge amount of data we had collected, and he decided to plot that up. And he got to me one day and said, there's something very strange going on in the fossil diversity. And we wound up writing a paper on that. This is a catastrophe we don't yet understand. There have been theoretical papers published to explain this 62 million year cycle in fossil diversity, but none of them hold up to my judgment. I don't think any of them really explain it. So you might think about this. But the basic plot was this. If you look at the number of, in this case, not fossil families, but genera, as a function of time, and time in these plots, in this case, starts here. We have time running actually the correct way on this plot. You see, there are times when the diversity is great, and then it drops. And it's great, and then it drops. Great, and when it drops. It seems to be a 62 million year cycle. And no, we don't know why. These are not mass extinctions. This has to do, and I spent some time with Dave Nelson today, and he's doing all sorts of things about how species compete with each other. I suspect it's something astronomical, because only in astronomy do you get 62 million year cycles that stay pretty much in phase with themselves. So I think it must be astronomical, but we don't know what it is. And this is not the 26 million year cycle. We've thought a lot about whether this is the sort of thing Lisa is working on, oscillations in the plane of the galaxy. We have not been able to make that work. Anyway, it's an unanswered question. While working on this, we became aware of a great deal of work that says, well, we knew. I mean, Walter Alvarez was one of the innovators in the field of geomagnetic reversals. What geomagnetic reversals mean is that the Earth is a giant magnet. You can use a compass because your North Pole is actually a south magnetic pole, which actually is attracted to the North Pole, or rather the North Pole of the Earth is actually a south magnetic pole, which is why the North Pole of your magnet points to it. So the North Pole is a south pole. But every once in a while, it flips. And when it flips, there appears to be something that happens in the fossil record. Animals seem to go extinct. Now, the standard theory on this is that when the Earth's magnetic field flips, there's a period when its field is very weak, and it no longer protects us from cosmic rays. That theory is demonstrably wrong. The reason is the surface of the Earth is not protected from cosmic rays by the Earth's magnetic field. It's protected by the Earth's atmosphere. And you can easily verify this by going up to the North Magnetic Pole, where the North Magnetic Pole offers no protection whatsoever against cosmic rays for physics reasons that a physics major can understand. And the intensity of the radiation is just a few percent higher than it is elsewhere. So what is it? Why are there extinctions when the Earth's magnetic field reverses? Now, I've been thinking a lot about impacts. So I had this interesting idea that maybe there was an impact. The impact triggered the geomagnetic reversal and also killed some animals. And so they were correlated, but they weren't causally correlated. They were both caused by the same thing. So I started thinking about this. How do I disprove this? How do I falsify this theory? How do I prove it's wrong? And geomagnetic reversals, this is a very crude picture of the liquid core, which is oscillating, rotates as it rises up from the heat. It tends to rotate due to the Coriolis force. This makes a dynamo that creates the Earth's magnetic field. The idea that and the number of reversals you get, this is the number of reversals versus time. If you look at this, you see there are times when there are a huge number of reversals. I think this is reversals every 2 million years. And you can see from 2 to 12 for 2 million years. But there's also this intriguing pattern. The pattern of reversals is used in geology to enable you to determine how old sedimentary rock is. So my thought was this. Suppose here's the Earth. Here is the liquid core. It's in here that you're generating the magnetic field. Suppose you had an oblique impact. Then the outer part of the Earth would start spinning a little bit faster. And that would cause a shear right at the core mantle boundary. Could that shear disrupt the Earth's magnetic field? I found a mechanism where it could, because material is floating up here, and it's forming little mountains on the inner side of this thing. If you started spinning it, those mountains would collapse, and it would be like sand that you'd pile up too steep. And when that happened, that would cause a change in the temperature distribution, which would disrupt the flow. The result is the Earth's magnetic field would turn off. It wouldn't flip, it would turn off. And then as things settle down, the magnetic field would build up again, but half the time it would be in the same direction and half the time it would be reversed. And that's consistent with what we know. We call them excursions if they're in the same direction, and flips if they're in the opposite direction. So I have a nice theory, but is there some way you can test it? So, I animated that. Okay, it spins the mantle, and that disrupts the core mantle boundary, and then that causes a change in temperature distribution, which causes the Earth's magnetic field to turn off. So I don't have flips. I don't believe there are geomagnetic reversals. I believe there are geomagnetic disruptions, and the data are all consistent with what I'm telling you now. And then it builds up, but half the time, more than half the time, it's in the same direction because there's a little bit residual left over. The few times it reverses, we call that a geomagnetic reversal. Okay, so that's that theory. So let me not go into that, but as I looked at the data, I said, I can make a prediction. This strange pattern, I'll bet you there was the biggest oblique impact of all time right where that blue arrow is. And that's why this pattern of hills, inverted hills at the core mantle boundary would be completely wiped out by a big impact. And if that happened, then you'd have to wait millions of years for the hills to grow up again, the ones that are responsible for triggering the reversal. So this is my theory. I'm sorry I'm going over it so fast, but I do want to get to global warming and air pollution. So I said, I predict that when you disrupt this, it would cause an instability in the mantle flow, which would cause a great outpouring of lava on the surface of the Earth. And let me look up. I knew there were lists of these lava flows, of these great flows. And after I had identified this, and I told Walter, I'm making this prediction, I'm going to look it up. And then I went and looked it up. Nothing. Zip. Nothing happened. Well, that kind of threw some cold water on the theory. So I wrote the paper, and here's a quote from the paper. There are long periods when there are no geomagnetic reversals. These could be a consequence of a very large avalanche taking place at the core mantle boundary. We expect there to be a very large plume of basaltic flow at that time, and then the killer. As far as we know, this prediction is not verified. There is no evidence of a strong flow at 120 million years. So this was the paper that I wrote. Very disappointing to disprove your own theory, but maybe there's some way around it. So I gave the paper to Walter to read. And I showed him this. And he said, Rich, what do you mean there's no large basaltic flow? What list did you use? I said, I used the paper of so-and-so. I said, oh, God. He said, you used a list of the continental basaltic flows. If you include an ocean flow, then the biggest flow of all time took place right there. And my reaction was, wow. Now, unfortunately, you write a paper like this, and the paper doesn't include a prediction. It includes a prediction I made and then verified, but there's no way the reader can know that I had written a draft of the paper that had the opposite. So I don't think the paper has gotten a whole lot of attention. This is it, avalanches of the core mantle boundary. I think this thing has great chance, and it's very hard to verify, but there are some ways it can be done. So I'm optimistic about this. But I like to tell people that I'm fundamentally an experimentalist, but when either I don't have much funding or something else like that, I'll dabble in theory, not real theory. I mean, not particle physics theory, but core mantle boundary, geophysics, that I can handle. At this point, I was looking for more catastrophes to work in. Are there other things that impacts could do? Nobody, when you're entering a new area of science, you want to see something that other people would have missed or not thought about because they didn't realize the importance, and asteroid impacts were one of them. And I wondered, could asteroid impacts cause the ice ages? So I read about the ice ages, I read about the standard Milankovitch theory of the ice ages, and I didn't believe it. I went to Gordon MacDonald, who's a geophysicist and an expert on everything geophysics. And I said, Gordon, I've read about the Milankovitch theories. I don't believe it. Can you give me a reference that will convince me that the Milankovitch theory is right? And he said, yes, I can. What reference? He said, one of my papers. Here, let me give it to you. So he gave me his paper, and it convinced me that it was fundamentally right. And I began studying it, collaborating with Gordon, who was such an enormous help. At one point I said, these guys use the Blackman-Tukey method of spectral analysis. I can't find anything in any modern book on Blackman-Tukey. Well, do you know what that is? He said, yes, it's the method advised by Blackman and Tukey in their book. And that's what everybody was using. And the people in this field all refereed each other papers, and they didn't have to explain what the Blackman-Tukey method is. I couldn't find anybody in statistics who knew what the Blackman-Tukey method was. But it's what's used in this field. Anyway, 10 years of research. And I wound up writing a whole series of papers on the Milankovitch cycles, pointing out that certain things are clearly wrong when you analyze the data in a truly objective way. Aspects of the Milankovitch theory, some things are really right. And this is another hour talk that I used to give. Wound up writing a technical book on the subject, which is widely used by graduate students around the world now on understanding ice ages and how you analyze them and how you look at these cycles and what is definitely proven and what isn't. And we came up with a whole bunch of things and an alternative theory, one of which I told Lisa about today, hoping she will look into it as a possible theory. We think the 100,000-year cycle of the ice ages is actually not related to the Milankovitch cycle, but related to a different cycle, which nobody had noticed had a 100,000-year cycle until Gordon and I did the work. So that's a side thing, but this relates to what's coming afterwards. Because after this disaster, I was really proud of this work, and I gave lots of talks around the country about ice ages and their astronomical causes and the Milankovitch cycles. Then I'd open up for questions, and people would say, so is global warming real? Well, that wasn't exactly what I was talking about, but people came because here was a physicist who seemed to know about climate, and they were asking the obvious questions about climate. And I didn't know the answers, so after that first session, I went home and I started reading about global warming. And I couldn't figure out whether it was real or not. I read some of the best papers on it, and I got totally confused. There were obvious questions that they didn't seem to address in their papers. So I tried contacting some of these people, but they didn't know who I was. Maybe I wasn't nobody. Maybe that's why they didn't respond. And I couldn't get any answers. In fact, they were being harassed by lots of deniers and skeptics who were harassing them with questions. I think in some cases actually trying to use up their time so they wouldn't have time to do any work. And they were just really annoyed by this. And so I couldn't get answers from them. So my next subject got into was global warming. This was made more urgent when my daughter and I, she was a international management master's degree. We started a consulting company, and we were asked by people in Bangladesh what they should do in order to mitigate global warming. And Elizabeth and I discussed this, And we didn't know what advice to give because I wasn't even sure global warming was real. And we couldn't get answers to our questions. And you don't want them spending lots of money, especially a poor country like Bangladesh, on something that isn't real. So Elizabeth suggested, why don't you put together some people and we'll start a nonprofit and we will investigate global warming and maybe you can answer the questions. Put together people who are really good at data analysis. Let's see if we can get the data. And at that time, there were some scandals that came out. The British team said that the data clearly showed global warming, but they couldn't release the data because they had signed some non-disclosure agreements, and they couldn't find the non-disclosure agreements. Therefore, they didn't know which data they could release, and therefore they were going to release nothing, which really infuriated some of the skeptics. Michael Mann had published a hockey stick plot, and then Steve McIntyre had analyzed that and shown that using Mann's flawed method of analysis, random data would always give a hockey stick. And I verified that he was right on that. So the famous hockey stick of Michael Mann, I don't mean global warming. Mann had gone back 1,000 years and showed this great hockey stick. And that was just, it was just a computer bug, a bug that happens to give a hockey stick. And so people, and Mann refused to admit publicly that this was a mistake. And so there were skeptics who were furious with that. And they too couldn't get answers to fundamental questions. I had a list of 5 questions that I couldn't get compelling answers to. And here they are. There were 3 other groups analyzing the data. They only used a tiny fraction of the data. One group used about less than 10%. Another group, the group that used the most, had about 15%. The data, they excluded a lot of the data. Was there a bias there? It could be. And I can tell you all about why it was plausible that there was a bias that would lead to global warming. There are things called urban heat islands, which we know are not due to global warming. They're due to the fact that people living in cities use more energy and it heats up the city. And they get rid of trees and things that tend to cool. So there was that effect. There's always bad data. I have a theorem that all great discoveries are made with bad data. People have always advised me, stay away from that. Your data, you're not going to be able to do it. And I realized, no, whoa, wait. If it's bad data, there may be something lurking in there that nobody noticed. And if you do it carefully, you can do it right. But they had manually adjusted their bad data. They said, well, this data point seems inconsistent with everything else, so we'll throw it out. And they hadn't kept records of that. So we decided we would automate it. We would look for things that were inconsistent with the surrounding areas, and then have it automatically programmed, keep a record of it, make it possible for you to put the data back in. It turns out all the data we threw out, if you put it back in, makes no difference. So we did those kind of checks. Most of the temperature stations were badly sited. We did studies of the good stations versus the bad stations and found out what badly sited doesn't mean badly enough to affect the measurements. And finally, when fitting it to these big global climate models, there were, well, anyway, we really came up with good answers to all of these. And to my amazement, we were able to do the study, and I thought we might be able to contribute to 2 of these, maybe. But we were able to go through all 5 of them. We were able to use all of the data. We were able to go back almost twice as far in time as anybody else. And we got one of the most beautiful plots in my life. And this is it. And this is a record of temperature from 1753 until the present. And the data itself are these thin lines. The gray lines are the uncertainties, and they're quite big back here, but not so big that you can't see the volcanic eruptions. The volcanic eruptions are known volcanic eruptions where we actually measure the dust in the glaciers of Greenland and Antarctica. So we could fit in these volcanic with one parameter, which is proportional to the dust that's observed. What about the rise? I tried various different things. I tried a parabola. Wasn't a very good fit. I tried an exponential. Wasn't very good. I tried the US population. Wasn't a very good fit. I tried a polynomial. No, I couldn't get a very good fit. So it was hard to fit. And then I was telling this to Robert, and he said, have you tried carbon dioxide? Oh, no. Let's try that. I guess I must have been a skeptic. So I tried carbon dioxide, and it's dead on. I came in the next day, I showed the group all the fits. I showed them the carbon dioxide fit. And I said, this is amazing. This is this is one parameter for the volcanoes, one parameter for the rise. I tried putting in the parameter for the solar variability. I tried putting in the solar variability, the known solar variability, in 6 different ways. None of them would contribute. We can rule out that the solar variability doesn't contribute to this to more than 5%. We could rule out that the volcanic eruptions all give these short-lived peaks. That's all they give. Carbon dioxide. So Robert was really happy that day. I think he believed in global warming all along. And I was converted. Global warming is real and it's caused by humans. And I have shown this to many skeptics. And there are different kinds of skeptics. There are the skeptics who I call the deniers. I'll show you a list of these different kinds of people. The deniers who think it's a big conspiracy and just to destroy the US economy, and I'm opposed to it. But then there are the skeptics who were like me, who said, well, I'm really worried about the urban heat island effect, and I can't get straight answers from these people. Or Michael Mann had this hockey stick, but it was a bug in his program. And these were thoughtful skeptics, what our statistician consultant called the properly skeptical. In fact, some people would say it's a scientist's duty to be skeptical. In fact, I would have fun at the physics department. People would ask me, do you believe in global warming? And I'd say, well, let me ask you, do you believe in it? He says, yes. I said, really? What do you think about the urban heat island effect? He said, the what? I said, the urban heat island effect. I mean, what makes you think the urban heat island effect isn't dominating this? I'd never heard of that. Well, then why do you believe in global warming? Oh, because it's a big conspiracy to undo science. Yeah, but when you talk about global warming as a faculty member, people think you're using your science. They think you are a physicist who has looked at the data, has come to some judgment, not saying you believe in global warming just because you've heard this conspiracy of people who are opposed to science. And that's the case of most people I know in the physics department at Berkeley. Most of them believed in global warming, but were unfamiliar with the issues that had been raised by the properly skeptical. Anyway, I now feel we have answered this. I'm rather proud of this. We were mentioned in the IPCC report. Didn't get really prominent mention, but I think the fact that we go further back in time and our uncertainties are about half as big as theirs. And up here, we analyze pauses and things like that. So we have a lot to say about global warming, but I want to move on. According to this, I've used 44 minutes so far. So global warming is real and it's caused by humans. What about climate change? Newspaper headlines today, the drought in California is exacerbated by climate change. Actually, not when I look at the data. I look at the data and I see no more variability in the temperature than we had 30 years ago. But here it is in the newspaper. Why? Because some scientist said it. How did the scientist know? I think he was probably quoting some friend of his. But the fact that a scientist said it means it gets into the front page of the New York Times. Here's a distinction I personally make. It's a difference between global warming and climate change. Global warming, which includes the rise of land and sea temperatures and the rise of sea level, this is real. I will put my scientific credentials behind this. I will argue it in any forum, and I will argue the statistics and the science, and most importantly, the systematics, the urban heat island effect, the data selection effect, all those things. We have done a good job. I will stand behind that and argue it in front of anybody. And by the way, I've talked to a lot of skeptics about this, and I've won over some very prominent skeptics. I'm not going to tell you who, because when I win someone over, I don't want them to think that I'm going to start blasting their name around as someone I convinced. But their names you would recognize. Okay. Is it bad? Yeah, probably. Is that a scientific conclusion? No. Why not? Well, it involves so many things. Economics, the human ability to respond. This is physics, that it's there and that's caused by humans. And I could rule out every theory that makes predictions. I can't rule out theories that don't make predictions. If someone says, oh, I think it's something else. Something else that just happens to match the carbon dioxide curve? Yes. What is it? Can you tell us? Well, no, it's just some random thing. Randomly, it happened to match carbon dioxide. I can't argue against that. We don't call that a scientific theory. Scientific theories are things that are falsifiable. And if it's not falsifiable, it's not science. It may be your theory, but it's not a falsifiable theory. It means it's not a scientific theory. Now, climate change is something else. Is there an increase in the variability of temperature? Actually, there is not. And even Jim Hansen agrees with this, despite the fact that everybody quotes his paper as evidence that it is more variable. But I've talked to Jim personally on this. No, he agrees. The correct interpretation of his paper is that the variability is not going up. There's no evidence for increased variability. There's no compelling evidence for increased droughts, for increased floods, for more hurricanes, more tornadoes. Here's an interesting plot that I made. I took 100 sites. I could find, there's a couple hundred sites in the United States, I think maybe 400 or 500, in which there's a temperature record going back 100 years. For each of those sites, I fit it to a straight line, just to see, is the temperature going up on average at these 100 sites? Get this interesting result. The red crosses are the areas where the temperature has gone up. The blue circles are where the temperature has gone down in the last 100 years. How can this be? Well, it turns out there are twice as many red crosses as there are blue circles. On average, the temperature has gone up. Now, this is not very scientific because it doesn't uniformly cover the United States. But I have the suspicion that most deniers come from the blue circle places. You cannot detect global warming yourself. You can't sense it. You can't walk out and say, oh, global warming. Because it's a small effect. Over the last 250 years, it's been 1.5 degrees. Over 250 years, you can't detect that. What about the increase in hurricanes? Well, there's been an increase in reported hurricanes, but now we report hurricanes out at sea, where we have buoys and we have satellite measurements. And if we go back to the previous big hurricane season, there were none out there, not even from ships. I think that's because the ships avoided that area, because it's a dangerous area. Suppose we take in physics what we call, in science, we call an unbiased subsample. Yeah, we'd miss things out there, but we're never going to miss one that hits the coast. So those are all reported. Let's see how many hurricanes there are that hit the US coast. And the answer is they're not changing with time. These are the average hurricanes, these are the bigger ones, and these are the giant ones. By the way, Hurricane Katrina was not a giant one. It was a medium-sized hurricane when it hit. It was a giant one out at sea. And in the past, it would not have been categorized as a giant hurricane. But it was because it was big out at sea, and then it weakens and it comes in and destroys New Orleans, but it was just medium-sized. But these are actually going down slightly. There's no evidence that hurricanes are increasing. There's no evidence the intensity is going. People search for a statistic, and the one they can find is if they take the most intense storms and what were the highest winds of the most intense storms, and that has gone up a little bit. But that's what they have to search for to find. We call this cherry picking, when you look around for some statistic that you can find and then quote. Actually, the number of hurricanes has been going down. Okay, so this is how I categorize them. You can each decide where you stand. They're the alarmists, the exaggerators, the warmists, the lukewarmists, the properly skeptical, the sarcastic skeptics, and then the deniers. And I would claim the following. There are two groups that ignore the science. And we can call the deniers anti-science, and that's true. But likewise for the alarmists. These are the people who say, I don't believe the IPCC report. I think it's much, much worse than the IPCC is willing to say. Well, they can say that, and they can think that. But don't think that's based on science. So let me give some names here. I just added this yesterday. I decided, hey, I could do this. So under the deniers, I will put down Ted Cruz. Now, there may be some Ted Cruz fans here. And if there are, I'm going to make you feel better in just a moment. Because I'm trying to be objective, not political. And I'm not telling you my opinion about whether I would vote for Ted Cruz. But he is certainly a denier. And if we want to find an alarmist, there's an obvious example, Al Gore. So you can't tell my politics by who I put on this list. Now, is he an alarmist? Al Gore film, An Inconvenient Truth, is getting wide distribution, and Vice President Gore made them available to every school in the UK. And a parent objected, said this is a propaganda film, it's not a science film. And so it wound up in court in the UK. And the judge asked people to come in from the Gore team to defend what's in there, and they asked skeptics to come in and to deny what's there. And the judge in the UK actually made a judgment. This is a court judgment. Those are the newspaper headlines. But he said that the Al Gore team could distribute the movie to every school in the UK anyway, provided it be accompanied by a list of 9 major mistakes in the movie. And that would have been a great thing. And I just wish people who watched the movie had this list. You can look it up online, or I can send it to you. The 9 major mistakes. One of them, I think, is not a mistake. But the CO2 rise is an exact fit. But these other things, the polar bears aren't dying from receding ice, and Kilimanjaro is melting because of farms that are built on the slope, not because of global warming, and a whole bunch of things like that in the movie. So he's clearly in the alarmist category. Meanwhile, I published, this is my op-ed in the New York Times, The Conversion of a Climate Change Skeptic. I showed you the movie, so I'm not going to show it to you again. This is a movie which goes every hour instead of every day. You can get these online at our website. You can download them, you can watch them, you can look up the recent temperature rise, you can look up your location. A couple days ago I looked up Cambridge. And this is global warming in Cambridge from 1753. Not surprisingly, you had some of the earliest measurements of temperature soon after the thermometer was invented. And here's the rise. So this is Cambridge. And it's not going to match the same as the average. Here's the average. But what can we do about it? So, last bit of my talk. What can we do about global warming? Do we need to do anything about it? Maybe not. But I'm worried because disruptive things, in Silicon Valley, disruption is considered great for the inventors, for the investors, but terrible for the competitors. I think things that are disruptive are usually bad, and I would like to stop it. I'm deeply worried about global warming. Now, looking at it objectively, look at it not politically, not on the feel-good measure, not which proposals being put forth by your favorite political party are the best. Think about it objectively. What can you do? As a scientist, the first thing you focus in on, where is the carbon dioxide coming from? And this is it now. The United States has actually gone down a bit, thanks to fracking, it turns out, because using natural gas instead of coal reduces the emissions. China's been shooting up. They're now at about twice the level of the United States. I've been told, don't show this publicly because you will be insulting China and will never get their agreement. But I think when you're a scientist, you have to look at it objectively and then let other people worry about who's going to be insulted. I personally don't think China is a bad country. I think we have to recognize, though, that if this trend continues, and this appeared in an op-ed piece I wrote, that China and the emerging are going to dominate. And here's the US, assuming that we follow the agreement in Copenhagen that was outlined at the time. So we're no longer in control of global warming. Anything we do that doesn't affect China doesn't count. It counts a little bit. If we would go to 0, then the total would drop by that much. And from the rise, in 4 years, we'd be back where we were. So we cannot stop global warming by disappearing. Pretty serious. When I was giving this talk, I would say, no, I don't know any solution. Now I have a solution. Here's one proposed solution, which was all hooray and so on, and I was enormously disappointed. I think all that happened is that President Obama agreed we would reduce, and China would plateau in 2030. In 2030, if their rate continues, and this rate growth, by the way, assumes a 4% improvement in energy efficiency. If this is where we will be in 2030, and here's the U.S. contribution. Yes. Yes. It goes against the 7 to 10% growth in their economy and use of coal. So they are seriously trying to cut back on coal. but this is what back several years ago I came up with. What it really says is anything that we do, oh, here are the evident truths. I have them here. Okay. If you aren't discussing China, if you write a paragraph and it doesn't have the word China in it, you are not discussing solutions to global warming. And you almost never see any discussion of China. Because you don't want to insult them, because then you'll never get agreement from them. But that means you're really not discussing anything. I mean, if you were to fill China with Tesla Roadsters, you would increase the carbon dioxide emission of China because those Tesla Roadsters will be running on coal. This is where they get their electricity. A second point, if it isn't profitable, it isn't sustainable, that's because China can't afford things that aren't profitable. But I think we can do it. And China's social harmony demands economic growth and pollution reduction, and that's a contradiction. China, I'm running a little bit late on time here. China is, they say it's a renewable powerhouse. A minuscule amount of its energy comes from solar. Most of it comes from coal. That's solar. 0.0006 is that nobody disputes these numbers. It doesn't stop the New York Times from saying it, or the Nature magazine, China's a renewable powerhouse, but most of their renewable powerhouse is hydroelectric. And I'm not a big fan of hydroelectric. Here's China's hydroelectric. Okay, they built a Three Gorges Dam. 1.2 million people were displaced, but the good news is they all volunteered. 13 cities were destroyed, 140 towns were destroyed, 1,350 villages were destroyed. This is all Chinese numbers, but the citizens agreed to it unanimously. Okay, and there are worse dams coming up. But solar, you must have read that China has greatly increased its solar last year. Well, their economy dipped a little bit, so they didn't have to turn on the new coal power plants that they had constructed. And most of their new energy source was coal power plants. 57% of the new energy was coal, 3% was solar. If you really think China is setting an example for us to follow, no, we have to set an example for China to follow, but it has to be an example where we don't spend money, no matter what the cost, we're going to spend the money. I'm going to buy a Tesla Roadster because it's ecologically good, and I don't care if I have to spend $80,000 to do it. I'm going to do what we need to do, but it's not an example that China can afford to do. So is there anything we hope? Yes, there is, ironically. There is something, and the hope comes from the horrific air pollution of China. That's a paradox, but that's what Elizabeth and I are now studying, and Robert, what we're now studying is the air pollution of China. Here's a photograph I took in Beijing. I call it Beijing Sunrise. It was from my hotel window. 6 months ago, Robert and I published a major paper on air pollution in China, published in this wonderful journal called PLOS, the Public Library of Science, PLOS One. I highly recommend you publish there. They are completely open. Anybody can download their articles, yet they are severely and seriously peer-reviewed, but they keep it on a schedule. They will not let you have to wait 6 months. They'll keep it fast. So they're doing it right, and I think it's a really good journal. This is our basic conclusions. It's a little bit scary. This is the average pollution in China. Everything you see which is bright green is healthy. Here are the numbers, and this is serious. And we published this, and it was covered a full-page article in the New York Times. It was a full-page article in The Economist. It was covered by just about everybody around the world, and nobody seriously disagrees with what we say. 1.6 million people die every year in China from air pollution, and you can see this in the death statistics from the sorts of deaths that they have. 1.6 million. That is 4,400 every day. That's a number that sticks with me, 4,400. You'll watch the news and someone will say, and so this boat overturned and 30 people died, and it'll be in the news for a week. And no one mentions that on every day of that week, 4,400 people died in China, because that's not news, because it happens every day. And it's spread out, so it's not in one place at one time. But I'd like to get people's attention on this. This is the greatest environmental catastrophe in the world today. Well, some people say, no, it's the water in China. Okay, well, that's bad too, and I haven't looked at that. But this is a real killer. This is 17% of the deaths in China are coming about from air pollution. And this is not a disputed number. It just isn't that well known. Every now and then there's a movie of China today, and here's the air pollution, and look how bad it is, and they really are, suffering. And we all look at it and say, oh, I'm glad we have good air here. And that's it. You forget about it. But we have 4,400 people dying every day, and we're basically not doing anything about it. 38% of the population is exposed to unhealthy air on average. On average. The Beijing air on a bad day is equivalent to everybody there smoking 40 cigarettes each, including children. That's on a bad day. The American University of Beijing has put up a circus tent outside of their headquarters with filtered air so that the children can play outdoors. We were able to do a lot in this paper. It turns out the real killer is something called PM 2.5, particulate matter, 2.5 microns and less in size. If you don't know about that, remember today, because this is the first you heard about it. I remember when Sterling Colgate said to me, Rich, I want to tell you about something that's called AIDS. And he told me about this new disease that attacks your immune system. And I remember that because later that became such a big part of the news. Well, PM 2.5 is going to be a big part of the news. By the way, you can go to our site online, and I even have something here. I think I may be online right now. And you can get an hourly update on the air pollution in the world. Right now, we're covering most of Europe. We're covering China. We're covering Vietnam and Japan. And you can do this. If you go to berkeleyearth.org and click on air pollution, you can see hourly updates. Because what we do is we download thousands of sites every hour on our computer. These are sites that are put up there by the Chinese. And they only leave them up there for a day. So we download them, but we generate one of these maps. This is PM 2.5. This one are larger particles, and you can see that's not nearly as unhealthy. And if you get down, in this case, to ozone, or NO2, or SO2, those are not the killers. The killer is PM 2.5. And we can even tell where it comes from, because we get hourly data, we can see this stuff move. And the remarkable thing here is that most of the PM 2.5 is not coming from Beijing. It's coming from south of Beijing and blowing north. They have managed to shut down most of the coal plants near Beijing. So, why can I be optimistic based on this? The reason is this. The particulates made by natural gas is a factor of 400 less than the particulates made from coal. If we can get the Chinese to switch and have their new development be all natural gas, then we can reduce the air pollution enormously. And the surprising, wonderful news is that cuts their CO2 emissions by a factor of 2 to 3, depending on which plant they're shutting down. So you can reduce their CO2 emissions by helping them switch and solve their air pollution problem. Now, I personally don't believe that China has high on their priority list global warming. Some of you may, you've talked to Chinese, I've talked to lots of Chinese, they always say they do, but I don't believe that. But air pollution is high on their list. And air pollution is high on their list because they worry about a particular kind of disruption, namely disruption of the rule of the Communist Party. And there are two things that can hurt that. One of them is lack of economic growth, and the other is pollution. And they're getting demonstrations all over China. If you use Google Chrome, you can get it automatically translated. You can read local Chinese newspapers. It's a wonderful, wonderful thing. And you can see they actually report these demonstrations. They have a huge number of demonstrations against pollution all over the country. Natural gas? You mean fracking? Yeah, I mean fracking. But fracking is bad environmentally. Okay, on our website you can download our careful analysis which shows why most anti-fracking literature is grossly exaggerated. One of the key things you need to know that most people don't bother to say is that the half-life of methane in the atmosphere from leakage is 8.6 years. And after 100 years, it is gone. It is really gone. It leaks some methane today, and it can have a big effect for the next 10 or 20 years. But in the long term, it is really gone, unlike carbon dioxide, which hangs around for thousands of years. So, I call this my Michael Dukakis photo. Some of you are old enough to know what I'm referring to. But this is at a site in China that is doing fracking. And I was there while they were fracking. I got to watch it all happen. Okay, what about nuclear power? My best estimate for the number of people who will die from Fukushima is 28. These long-term cancers. They evacuated. Most people got out. And this is based on the Japanese numbers and based on the linear hypothesis. And I have no threshold in here. It's just what's going to happen. And I've shown a lot of people this numbers. I ask people who are experts on this, I say, so how many people do you expect to die from long-term cancer, Fukushima? And from the experts, they usually say, oh, less than a couple hundred, or maybe less than 100. Most people know there's not going to be long-term cancer from Fukushima because the people were evacuated in time, and now they're being let back in little by little. But it's not a and nuclear waste. It was mentioned that I have another hour talk on how we solve nuclear waste. Basically, I believe that there is a solution to nuclear waste, which is to bury it 2 miles down in boreholes. And I think that is something that really is realistic and something that I can defend in great detail. So nuclear is going to go ahead, even if we don't. If the United States and Japan says we're not going to build any nuclear power, then the world will still get nuclear power. I predict that 30 years from now, 40 years from now, you can go to Africa and you'll discover, wow, they have constant electric power. It's on all the time. How did they do that? They'll say, our power plant is over there. Where? I don't see a power plant. Oh, it's buried underground. Your power plant is buried underground? Where? Right here. Oh, wow. Down there? Who's operating it? Nobody. It just takes care of itself. It's called a battery. Real battery? No, not a real battery. It's a nuclear battery. It's what's called a 4th generation nuclear power plant. It doesn't require anybody watching it. It can't melt down for physics reasons. What's this on it? Oh, that's a label. You wipe it off. It says, made in China. And that's the world we're heading to. Because China is building 32 nuclear plants. We're building 2. And they're going to surge ahead on this. And they're going to dominate the world. If you're worried about nuclear proliferation, don't worry. I'm sure China will be very careful with the nuclear reactors that they hand out all around the world. So anyway, there's a whole story on nuclear power I could talk about, but I won't. I'm going to just wind up with a relatively light note. And I visited China many times in the last few years. One trip I went to Chengdu. No polar bears in Chengdu. But for people who are worried about polar bears, I say there is another cute animal that I think is more endangered than the polar bears. The panda. Panda is cute and lives in the middle of this air pollution. Their forests are in this air pollution. The place where they breed them is in the middle of this polluted area. We are killing the pandas. We may not care about 4,400 people today, but what about the pandas? So I'm going to show a little movie here. There's me. Oh, watch his hand. Look at his hand. So, and you can do this if you go to Chengdu and call me and I'll tell you how to arrange it. And here, play the movie again. Watch his hand. Watch his left hand. Look at that. He puts it, I showed this to my granddaughter and she said, Grandpa, why are you wearing gloves? Anyway, some people say I was lucky he didn't bite off my nose. But hey, we can fight global warming and at the same time, we can save the pandas. So let me end with that. Thank you very much for your attention. Careful. Yeah.
Stay here. We'll take some questions.
Sure.
How much time do we have? Okay.
Thank you very much, Rich, for really fascinating and partly really controversial talk. I hope there will be a lot of questions from the audience. And wait for the microphone. There are two people with microphones. So first over there. Yes, please.
Hi, thank you. From your chart showing the global temperature change over time, it looks to me like there was huge variation from 1750 to 1850 compared to the time after 1850. Could you tell us why that is, or am I mistaken?
No, you're right, and we think that's largely due to the volcanic variations plus the large error bars. So if you look back then, it's possible that the variation was larger. Let me just find that plot here. That's right, it wasn't near the beginning of my talk, it was near the end of the talk. Here it is. Okay. Oh, no, that's not it. Well, actually, this is an interesting plot, too. This is the one for Cambridge, and I can show that. So, slideshow, presenter view. And here, it's not quite as dramatic. Maybe because the data are not as good as when we have the entire Earth. But there is this whoa, 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 which there is a whoa, and then not much, just a rise. And that kind of variability, we think, is almost certainly due to variability in ocean currents. So if we look, there are several well-known oscillations, the most famous of which is El Nino. But that takes place on sort of a 5 to 10 year cycle. It's not perfectly periodic, but neither is this stuff. There's the North Atlantic, something called the conveyor belt, in which there is a point in the North Atlantic where the conveyor belt goes from the surface, from the Gulf Stream, goes down and comes back under deep. But just where it turns down varies back and forth, and it has about a 40-year cycle. And that is probably responsible for this bump. Back here, there are things like the North Pacific Oscillation. There are others. So the ocean is modulating this. And I think of this as there are two things going on. There's the rise, which is such a good match to carbon dioxide, and there's something else which we could fit it with a bunch of parameters, but I don't think that we'd learn anything from that. My guess is that this kind of variation is largely due to, here's the other plot. Okay, and you were referring to this spikiness here. But the error uncertainties are really large on this because we're giving much finer resolution. If you average it out, as I did in the previous plot, then you don't see that spike so much. This is what we believe is the average behavior in dark.
Yes, you went through the one page where you about fracking. You went through that very quickly.
Oh, yeah.
And I'd be interested in knowing some of the reasons why fracking isn't as bad as people think.
Why it isn't why I think it isn't as bad as people think. Again, I have a paper on this online, but that's worth going through.
Particularly worth the water, the effect on the groundwater and things like that.
Yeah. Okay. There's a famous movie about flaming faucets, which you can get on YouTube, in which someone has a well nearby, and due to fracking, when he turns on his water, he can hear things coming out, puts a match there, poof, it lights. And so the state of Pennsylvania looked into that and studied it, and they went there. And you can actually determine whether natural gas comes from fossil fuel, it has no carbon-14 in it, or whether it comes from the surface water, which is full of carbon-14. In this case, it came from surface water. So his well was contaminated because there were bacteria in the surface water. And you could show this was not due to fracking. So the groundwater contamination, there have been a few places where groundwater has been contaminated. And the best thing you do is you find companies that do that enormously. And yes, you can do that. And it's mostly the wildcatters who go in there quick to make a quick buck who do that. Once you get the big companies going in there, they are enormously careful. And I've seen their things. So I'm not worried about the groundwater. The depleting fresh water. Well, in fracking, People in Texas use fresh water because the ranchers insist on it because they get paid big bucks for that. You don't have to use fresh water. You can go down 1,000 feet. There's brine down there, which has no, and I have maps of the brine I can show you. There's brine in basically every fracking region. You can use that water. Apache Corporation now uses nearly 100% brine. They don't use up any fresh water anymore. You don't have to. I've lectured on this in China and told them they are worried about running out of fresh water. I'm telling them, read these papers by Apache. You don't have to use fresh water ever. Pollution of aquifers. And again, just if you require best practice and you require the right kind of drilling and so on, basically all the bad things that have been done were either done 20 years ago and they show leakage, or they are done by the wildcatters. So I think that can be done. And that's a lot easier to do than to develop some new technology that isn't yet cheap enough for China, but can be. I think require best practice. Earthquakes, it turns out earthquakes are not due to fracking. Earthquakes are due to the disposal of the fracking fluids. And when they get the fracking fluids, they've been pumping them into vulnerable sites, and they're putting way too much in and pumping them at high pressure in sites you never should do, and that's easily avoided. So we can avoid that in the future. The fusion of methane issue, as I said there, it has an 8.6-year half-life. And so it is a problem if you get big leakage. If you get a few percent leakage at the 8.6, it's 80 times worse. And so for a few years, it is worse if you get that much leakage. You can hold that leakage down. And I think, again, when you're rapidly developing something, people tend to go for the quick profit, and they're not careful. But we can monitor that, and we can hold that down. And finally, we worry about the air pollution from fracking. It's tiny compared to the air pollution of coal. So that's my quick overview. So I really your answer deserves at least half an hour. And we have some papers online at berkeleyearth.org that will go into these in more detail.
I just want to follow up on the fracking issue. I heard that there's a technology in the future that there will be dry fracking.
That will be what?
Don't have to use water. The dry fracking.
Oh, dry fracking, yeah.
And
Yeah,
so
I know all about that technology. You could use carbon dioxide gas, for example, and you can sequester some carbon dioxide at the same time. There are other gases that you can use there. And those are fine. But the fact is, brine works fine. And it has no commercial use, and it's at all these locations. So I wouldn't invest in a company that had an alternative, because there's a real cheap thing that'll put them out of business. People will go with the brine. But yes, those things will work. They're just more expensive.
What's your opinion on nuclear fusion energy as opposed to fission?
Well, if you'll forgive me for making the standard joke, it is the energy source of the future and always will be. I know a lot about it. I've been on the technical review board for the Lawrence Livermore Laboratory, and they were making all sorts of wild claims that I had to calm down, because they were making optimistic statements about how cheap their pellets will become that I just don't think were realistic. They finally closed down that operation. They're not going to try to make it ad Livermore from pellets as they had been advertising they would. I think the tokamak is coming along at a good pace, and I can only make predictions reliably 10 years ahead, because I know what technology is online, and sometimes I can guess correctly 20 years, and beyond that I can't guess. So I think the best hope for fusion is one of these unexpected breakthrough disruptive technologies, maybe Tri-Alpha. I don't know if you know about Tri-Alpha, but it's a stealth company that's been publishing some papers recently, and they have a superb team that's doing it. And my guess, some company like that is going to have some sort of breakout, and then we'll have fusion. But it's not a whole lot better than fission. The people are opposed to fission because of all the waste problems. You put it 2 miles down in a borehole, it's no problem.
In your list of contemporary issues that concern you, you mentioned nuclear energy, and you debunked that. What about nuclear war? I'm kind of worried about it. I'm waiting to be reassured by you.
Well, know a lot about nuclear weapons. I had all the right classified clearances and so on. And I have friends who know as much as I do, and we feel very differently about nuclear war. They still think it's the biggest danger out there. I don't see it as a big danger. I don't think terrorists can do it. I think they might be able to steal a nuclear weapon. I worry about them stealing nuclear weapons from Russia, from Ukraine, from the Soviet Union. But it's really hard. Those have, I mean, as for making their own nuclear weapons, that I find rather implausible. North Korea, and I argue with these other expert friends. Paul Horowitz is one of them, and you can talk to him. He knows at least as much and probably more about this subject than I do. But it's not easy to make a nuclear weapon. If you want to make a uranium weapon, then it's heavy, and you have to get the purified uranium. And I'm not in favor of letting 90% uranium wander around anywhere. These four. The what? Command and control. Yeah, well, that's where I worry about the Ukrainian and former Soviet Union nuclear weapons. We don't have all those accounted for, and that's my big worry. I'm not that worried about people making nuclear weapons from reactor waste. I think that is enormously difficult to do, but I do worry about something being stolen. And I'm not that worried about North Korea. Their nuclear weapons are not. I don't. Again, we disagree with some of my expert friends, but personally, I believe those tests have been done to give an enhanced and exaggerated seismic signal because the North Koreans want people to think that their nuclear weapons are bigger than they really are. I think they've all been fizzles. Anyway, it's a big subject, and we could talk more. I can't really put you at ease because I think the stolen nuclear weapons from the former Soviet Union is a serious problem.
Coming back to nuclear energy, in India, they're trying to develop thorium as opposed to uranium,
Right.
which gets rid of a lot of the problems of burying, etc. And second of all, since it's in India, isn't India going to be as big a polluter as China, and what about that?
Oh, I'm strongly in favor of India developing its thorium reactor. I don't advise people in the United States to develop it, and there are several reasons for that. The thorium reactor does produce less in the way of radioactive waste, but I don't think radioactive waste is a big problem. You put in these boreholes, and it's basically gone. The ground is already radioactive. We live in a radioactive world. The storage problem, I think, is an exaggerated problem that does have technical solutions that are relatively inexpensive. So I'm not that worried about the nuclear waste. The nuclear proliferation issue, they say it doesn't use uranium-235 and therefore you can't make bombs out of it. Yeah, but the first thing you do with thorium is you convert it into an isotope of uranium, uranium-233, from which you can make nuclear weapons. And that happens in all these reactors. You don't actually have fission in the thorium, you have fission in the uranium you made from the thorium. So I don't think the proliferation issue is a real advantage. As for the amount of thorium, India has huge amounts of thorium. Right now, if you look at the cost of uranium for our nuclear reactors, it's down at about 0.1 cents per kilowatt hour for the cost of the uranium. If you were willing to pay 0.2 cents, now this is where the average cost per kilowatt hour is 10 or 15 cents. If you're willing to pay 0.2 cents for the uranium instead of 0.1, the amount of uranium is 6 times larger. We're not about to run out of uranium. So I don't see any compelling reason for thorium. I see nothing against it, but I don't think it's something where we should switch over to it necessarily.
You keep mentioning boreholes.
Yes.
10,000 feet down.
Yeah.
How big do these holes have to be?
9 inches.
And how much are you going to contain with that?
Oh, basically a reactor lifetime.
In a 9-inch hole?
Yeah.
It has to be cased, of course.
Yes. That 9 inches is inside the casing. That's right. We've applied for a patent on this, and there are a bunch of things I'm not mentioning right now. So Yucca Mountain would have worked fine.
Okay. Frankly, I don't believe you.
Good. I don't want anybody reinventing it independently.
Staying with nuclear power, which is the perception nowadays, and rightly or wrongly, is that's nuclear power is bad. But is their reactor design similar? Are they using boil water reactors, or are they doing a different reactor design? And would a different reactor design help the economy of nuclear power?
The reactors under construction in China are the Westinghouse AP1000. So they're building U.S. reactors. They're licensed to do that. They will soon be building their own, but right now they're building U.S. reactors. It's a very safe reactor. I mean, I've always felt that reactors are sort of a little bit on the margin, but not as bad as people say, because life is dangerous, and if you want complete safety, then don't use energy. But the AP1000 is the best reactor around. It is much, much more safe. It has convective cooling for the first few days after, and the way they're building. I was at a reactor in Japan in which they built a 70-foot wall around the reactor. I looked at this and I said, I got to look up the number when I get back. I looked it up. Sure enough, it's 10 feet higher than the wall that they put on Skull Island to keep King Kong out. And they have this reactor around it. And I said, why are you building it so high? There's no tsunami expected here more than 20 feet high ever. And they said, well, building it 70 feet high, it only cost us $1.2 billion. I said, that's a lot of money. And they said, oh, no, it's not. For every year that we have this reactor turned off, we are spending $1 billion a year in liquefied natural gas to replace it. So $1 billion is nothing. If we build a 70-foot wall and it reassures the Japanese public that this is safe against tsunamis, then we win. I think the Japanese are not telling their public yet that they're going to really go on back on nuclear full speed, but they're preparing them for it.
One last question. What about potential, innovative designs of the nuclear innovation? Like, I think I think I heard you correctly. It's going to be under the ground. No one's going to have to maintain it.
Look up on Wikipedia fourth-generation nuclear plants. And what you will find is that there have been very smart people, very good people working on these things. Their designs are beautiful. They're the things you can do now with computers that you couldn't design 30 years ago. But you can't license them in the United States.
Okay.
And the reason you can't license them is that the Nuclear Regulatory Commission hasn't yet worked out how to license them. So nobody will invest in them because you can't get them licensed, because the NRC promises they'll speed this up and get it okay to license, but they haven't really begun yet.
Right. So for those designs, did you imply that China is moving full speed ahead?
No, they're not moving ahead on those yet, but I expect they will.
Okay.
Right now they're using the AP1000s.
Okay. So what would be the timeline of that transition at a technical level, if there weren't political issues?
I mean, the problem with nuclear power, a lot of people say it's expensive. It's expensive up front. And then it is very low for fuel cost. That's the 0.1 cents per kilowatt hour. Very low for operational cost. It's very reliable, over 90% capacity factor these days. So I believe that China they're building or have plans to build 32 of these. That's a pretty rapid expansion. And I think in the next few years that number is going to go up. And then they will start soliciting fourth generation. My guess is they'll be the first ones where fourth generation will be built by US companies. And that they'll start having those there, because they will make it possible for you to license them. We can't get them licensed in the US. But I think they're going to go ahead full speed. Their government has basically convinced their public that nuclear powers are safe. And our government has done the opposite. I like to think the U.S. should set an example for the developing world. And one thing we're doing we're doing a good job on energy conservation. We keep on improving. We're getting good at that. We could do a much better job. We need to do a much better job because there's so much room for energy conservation. On fracking, we're setting an example that everybody wants to follow. And there are environmental issues that people haven't settled down on yet. They're still afraid of it. And it turns out, I know a lot about the fracking business, it's not moving ahead anywhere right now outside the US. They're trying to do it in China, but they have political problems in China. Nuclear power is something where there's a wonderful movie called Pandora's Promise And in Pandora's Promise, you have one environmentalist after the other coming on and saying, well, I oppose nuclear power, and I oppose it for the following reasons. There's this danger, this danger, this danger, and this danger. Then another environmentalist comes on and says why he opposes it. And then another environmentalist. These are famous environmentalists. And then 10 minutes into the movie, they say, the same environmentalists come back and say, no, here's why I now think it's necessary. And why I think this issue is solved and this issue is solved, and we really need it to prevent global warming. And I would add in air pollution.
With that positive note, let's thank
Thank you.